Hey guys, so there you go. There's another corny circle song. You guys can put your hands down now from drawing the circles in the air. In 10.3, we're using chords. So we're going to use the chords to find some lengths and arc measures in our circles. First, take a look at a little cartoon that I found. Here's one. The guy's getting an MRI, which means he's getting basically a picture of what's going on in his head, but screaming inside there, and says, one doctor said, "I tell you, work has gotten so much more fun since I hung that rubber spider in there." Oh man, I've never had an MRI, but my wife has, and she does not think that those were not pleasant experiences for her. Alright, let's go on to look at using chords of circles. So let's remember what a chord is. A chord, again, is just a segment that's going to intersect two sides of a circle. And if that chord goes through the center of the circle, then that chord is a diameter. And if it is a diameter, then it creates two arcs. They're both semicircles if it's a diameter. But if it's not a diameter, it's just a regular chord, then it creates two arcs. One's a minor arc that's going to be less than 180 degrees, and the other one's a major arc that's more than 180 degrees. So that's what this is all talking about right here, which you can kind of read through there, but I just kind of explaining that. Our core concepts now, there's on page 290, 291 have these theorems, and these are the theorems we're going to be looking at in this lesson. So our 10.6 theorem, congruent corresponding chords theorem. So what this is saying is that in the same circle or in congruent circles, so you could have it in congruent circles. There could be two circles that are at least told to us or shown to us that they're congruent, and it could work there too. So if you have two minor arcs are congruent, if and only if their corresponding chords are congruent. So if you have two chords here and those chords are congruent, then the corresponding minor arcs can also be congruent. A perpendicular chord bisector theorem. So this is if a diameter of a circle is perpendicular to a chord. So it's going to be, the diameter is going to be going through the center, of course, so we're going to see that as a diameter. And if it's intersecting a chord and at a right angle, where it's showing it's perpendicular, then what we can know is that it bisects the chord and its arc, which means that these right here, F to H and D to H, those two pieces are going to be congruent. Also, these are going to be congruent as well. The arc F to G and the arc D to G will also be congruent as well. So you have parts that's going to bisect this chord right in the middle here at H. It's also going to bisect the arc right there in the middle at G. Then the converse of that last one, the converse is kind of like the reverse of this last theorem. If one chord of a circle is perpendicular or is a perpendicular bisector of another chord, then the first chord is a diameter. So basically what we have here is if you have two chords and there's no center point shown on this one. So you just see two chords. And if you can see that they're going to be, one's going to be bisecting the other chord, and it shows here it's bisecting and it's perpendicular right here, then what we can conclude is that this chord here from Q to S, that's going to be a diameter. It's going to end up going through the center point. That's what we can conclude. We know definitely that these arcs are also going to be bisected, of course, but what we can also know is that this is going to be a diameter. Alright, let's take a look at a couple examples here. So this first one, just go ahead and watch this. Now this is congruent circles. They're two separate circles, but they are shown and told to us right here. They're told that they're congruent, and they're also in the diagram even shown to us that they're congruent because the radiuses are congruent. If they have the same radius, then they're going to be congruent circles. So in congruent circles, we have two chords that are congruent. It shows us that they're congruent. So this chord right here, F to G, is congruent to this chord here, JK, and that's what it tells us right here as well. And it says also that the measure of this arc here, the measure of the arc of JK, is 80 degrees. So then it wants us to know, well, what is the measure of this arc? So we just know it's the same thing as JK. It is 80 degrees. So that's what we can see here, because those arcs are going to be equal to each other. The measures of the arcs will also be congruent if the chords are congruent. Here's another one that's got two things on it, one diagram. So it's showing us that this is a diameter. It's going through the center point, and this chord right here is showing that it's perpendicular to that diameter with this right angle. So what we know now from this is that this chord is bisected at the end here, two equal pieces. So on this side it's also 7. And then this arc is also being bisected here at the J, so these two expressions are going to be equal to each other. So the first thing it says find HK. HK would be the length or the measure of that chord. So if you know this side's 7 and that side's 7, then the whole thing is 14. So that's what it's showing you right there. The HK is 14. And then it wants us to find the measure of the arc from all the way from H to K. So we're going to set these two equal to each other to figure out, well, what is X first? And so 11X is going to equal the 70 plus X. So that's what it's going to show us here. 11X equals the 70 plus X. Solve that, so subtract the X to get 10X equals 70. Divide by 10, so X is a 7. So we can plug that back into either one of these. If you say 11 times 7, that's 77 on this side, which means this is also 77. So adding those together, or 2 times 77, is 154 degrees. So that's the measure of the arc from H to K. All right, let's go on to the extra practice now. On the next page, page 292. Okay, so 1 through 4, it says find the measure of the arc or chord in circle Q. So remember, we name it circle Q because the center point is labeled Q. So the first one, it just says find the measure here of the arc of WX. So WX would be right here, this piece right here. We're trying to find that arc. So it tells us a central angle on this side. This is a central angle, so 42 degrees. So what we know there is if that's 42 degrees here, we know that this arc right here is, to find the measure of this minor arc, it's also 42 degrees. We know that. It's something we can definitely say. But is this over here the same thing? Well, it is, because what we have here with these two diameters, you have a diameter going from W to Y and from X to Z. These two diameters actually create vertical angles. Vertical angles are always congruent. So if this is 42 degrees here, then we know this central angle on that side is also 42 degrees, which would mean that this arc up here is also 42 degrees. So that means our measure here for problem number 1 is 42 degrees for that measure of the arc WX. Number 2, what's the length then of YZ? Just YZ here. So that's going to be just this little piece right alongside here. So in this case, if these arcs are the same, so we could say, well, if the arcs here are congruent, then the chords that go from WX here and Y to Z, that those are also going to be congruent. So if this is 3.6, then we know that the other one is also 3.6. So that means our YZ is 3.6. And then number 3, we're looking for the length of WZ. So WZ is this length right here. And for this one, we don't, we do know the length of X to Y. Now, is that the same thing as W to Z? Well, let's know this. We have, again, this central angle on this side is going to be congruent to the central angle on the other side because of vertical angles. So that means that if this arc or this central angle means that's going to be the same measure as this arc from X to Y. So that means that this arc also will be the exact same thing, because these are going to be congruent. These have to be congruent arcs because they're going to have the same central angle. So that means those two are going to be the same. I'm just going to put X's there to show that they are the same. If this is X on this side, that's X on the other side. We don't necessarily know what those are yet. But now what we do know is if we have congruent arcs, we're going to have also congruent chords here. So the chord from X to Y has got to be congruent to this chord that we're trying to find. So that means that our WZ is 9.2. We can definitely conclude that. And then number 4, we're looking for the measure of the arc x, y, so that would be this arc here. So if this arc right here, it's the same as this arc on this side, but how do we figure that out? Well, it's we could see that it is, partly of a circle here. We can see the whole. We can either make an equation for the whole circle or even just half the circle. We could use a diameter. Either way, I chose to use the whole one, and that's fine. So if I just added everything up around the outside here instead of equal to 360, because 360 degrees is the whole thing. So there's two x's, that's 2x, 42 and 42 make 84. So 2x plus 84 equals 360, and then just solve for x here. So that would just be subtract the 84 from both sides. That's 2x equals 276, divide by 2, x equals 138. That's the same thing as if I did just do 42 minus 180, because this we know is 180 degrees for the semicircle, because it's a diameter. So that's another way you could have done that even maybe faster, is just saw that as, here's a diameter, that's 180 degrees. So you could have set an equation up there, x plus 42 equals 180, and subtract 42, and you'll still get 138. So either way, you're going to get the same thing, 138 degrees for number 4 here, the measure of arc x, y. All right, let's go on to the number 5 next. Okay, for 5 and 6, it says find the value of x. And so those are the theorems we were talking about with the diameter and a chord that's perpendicular. So that means that we have a bisector here. We have this chord is being bisected at this point at T. The arc is also being bisected at this point at Q. It gives us that this piece right here from TP is this expression, 2x minus 4.1, and over here TR is this expression, x minus 0.5. Those two are going to be congruent, so we can set those two equal to each other to set up an equation and find the value of x. So the 2x minus 4.1 is equal to x minus 0.5, and so we'll get the x's together. I'll subtract x from both sides first, so that's just going to give me now x minus 4.1 is equal to a negative 0.5. So make sure that is now still a negative 0.5 here. We now want to add 4.1 to both sides, and when we do that, we'll cancel out this, and we'll just have x on this side. So we're going to take 0.5 away from 4.1, and that's going to end up giving me x is equal to 3.6. So there's my value for x on this one, number 5. Problem 6, we have the same situation happening. So here's just another one, same exact thing. We're just going to set those equal to each other. Why don't you go ahead and stop the video and try that problem, and you should be able to find the value of x on your own. Okay, so hopefully you did stop the video real quick, and I'll just show you what you should have put down. We're going to set these equal to each other. 2x plus 1 equals 3x minus 5, and I'm subtracting the 2x first on both sides, so that gives me a 1 equal to x minus 5, and just adding 5. So here x is just equal to 6. It's that simple. So that should have been no trouble on that at all. All right, let's move on to the next part. I think we're going to do a little joke of the day. So our question here is, who lives in the scary 100-acre wood? Well, that would of course be Winnie the Pooh. So there you go, Winnie the Pooh. Alright, well, next theorem there on page 291 is the equidistant chords theorem. And so for this one, it says in the same circle, or it could be congruent circles as well, two chords are congruent if and only if they are equidistant from the center. So that basically means we know that these two chords here can be congruent, AB and CD, if these two are going to be equal to each other. So they have to be at a distance. That's why the perpendicular marks are here. Their distances have to be the same. So it has to be a distance, equal distance from there. So the distance would always be at a perpendicular when we're talking about that. So if these are the same, if these are equal to each other, then we know these chords are going to be equal to each other as well, congruent. Alright, so 7 and 8 is find the radius of the circle. And first thing you're probably wondering is I don't even see a radius in our circle. So what we're going to need to do is actually draw a radius. A radius is going to go from the center to a point anywhere on the circle, and so you can pretty much choose any one of these points, A, C, D, or F, to go to. You just want to draw a line from P to one of those points there. You definitely want to choose those points because those are all already points on the circle. You don't want to go from here to just some random place over here. That won't help us. So I'm going to choose to go to C over here. So I'm just going to put a radius right there. So from P to C, that's our radius. That's what I'm trying to find on this one. So what that creates for us is it creates, because in this diagram it shows P to B right here is perpendicular to chord AC. So what that creates is a right triangle. And so now we remember things from right triangles, Pythagorean theorem we know. If we know this piece right here is 3, and we can figure out what this is here, then we can find R using Pythagorean theorem. And so that's what we're going to be trying to do here now, is first figure out what's the length of really C to B. Now what I do know here is that this chord AC is 5x minus 2. This chord over here, D to F, is 3x plus 2. So because these are equal distance here, these chords are both equal distance from the center point. That was that last theorem we were just looking at, the equidistant chords theorem. Because these are both 3, that means that these chords are equal to each other. So we can make our equation out of setting those two equal to each other, and we're going to say just 5x minus 2 equals 3x plus 2. Solve for x, that's the first thing to do. So we're going to start by just subtracting 3x from both sides. So that's going to give me now 2x minus 2 over here, plus the 2 on the other side. And so now I'm going to just add my 2 to the other side over here. Adding 2 will give me a 2x now on this side and 4 on the other side. So I'll have a 2x after I add 2 here. So 2x equals a 4, divide by 2, and we know x is 2. So now that we know x is 2, I can plug that into right here, 5x minus 2, to figure out what the length of this AC is. So it's going to be 5 times 2 minus 2. Let's just go ahead and plug that in. So that's going to give us 10 minus 2 right there, and then 10 minus 2 would be 8. So the length of AC is 8, and what we do know is that this right here, this point B, is actually it's a perpendicular bisector to chord AC. Now remember that radius right here, now if I kept on going with P all the way to the edge of this circle, that's a radius. That's going to go through our center point. And this chord here is also, connecting that radius there at a right angle. So that does mean the same thing as we learned before, that this is going to bisect then this chord. So that means that these two, A to B and C to B, are both exactly equal. So that means that we can say BC now is half of 8, which is just 4. So now that we know that's 4, this is 3, we can use our Pythagorean theorem. So A squared plus B squared will equal C squared. That's the R squared. So it'll be 3 squared plus 4 squared equal to our R squared. So we're going to say, well, 3 squared and 4 squared, that's 9 plus 16. And 9 plus 16 is going to be 25. So we're going to now take the square root of both sides here to solve for R. To get rid of our square, we're taking the square root. So the square root of 25 is just 5, so R is equal to 5. There's our radius. That's what we found. All right, you can go ahead and pause the video and do the same thing on number 8. Go ahead and try number 8 on your own, and then start it again to see if you did it correctly. Just go through exactly the same steps as we did on number 7. Alright, so hopefully you paused the video, and now let's just go ahead and check to see if you did number 8 correctly. We're going to go ahead and draw a point. I should have actually told you which point I'm going to draw it to, I suppose. That would have been helpful. You could still get the same answer, though, anywhere you draw it. So I'm going to go from this O point to either U, V, W, or X, and I'm drawing it to W. If you drew it to one of these other ones, you could have got the same exact thing. So it doesn't really matter. So we know, okay, we're trying to find this R right here, the radius. So we need to figure out, okay, what is this segment and also what is this segment here. So we know W to Z, and we also need to know what this O to Z is going to be. Well, it does tell us that this chord, W to X, is 20. And if this, again, like we saw over here, was a bisector, so that means that WZ is exactly the same as X to Z, and if the whole thing is 20, half of 20 would be 10. So we know right there that that side's 10. So now we just got to find out what the O to Z is. And so again, because these chords are equal distance here, we know that these, because they're both at a distance, they're both from the center to each chord, those have to be also exactly equal. So it's kind of like almost a converse of this other one. So these are equal, so we could set these two equal to each other. I'll just put a little equal sign in the middle. Just hang on. So if these are equal to each other, then I'm going to subtract my x. Just go ahead and solve this. Subtract x, it's going to give us 3x minus 5 equals 4. And add 5, it's going to give us, I'm going to add 5 to both sides. 3x is equal to 9. And then, of course, we divide by 3. 9 divided by 3 gives us x equals 3. So now if x is 3, we can plug that back into our x plus 4 here. So 3 plus 4 would give us now 7 then for this side. So now we can use our Pythagorean theorem. A squared plus b squared, which is the 10 here, equals c squared, which is the r. So I'm just going to put up on the top 7 squared plus 10 squared equals r squared. So that's a 49 and a 100. So 49 plus 100 is 149, and we're going to take the square root now of both sides. The square root of 149, that does not come out to be perfect. You'll see it's going to be 12.2 and then it's a bunch of decimals. I'll just go 12.2 is fine. So we'll just say our answer there is approximately radius is 12.2. Alright, one more I did want to show you before we leave is just this last one. It says 3 bushes are arranged in a garden as shown. Where should you place a sprinkler so that it is the same distance from each bush? And so they're going to draw a little diagram here. They're going to have the bushes A, B, and C. They're labeling them. They're going to connect the dots there. So it says label the bushes A, B, C as shown. Draw segments A, B, and B, C. And then the next thing they're going to do is they're going to say, okay, draw perpendicular bisectors of AB and BC. So we're going to make a perpendicular bisector here and here. We've done that before back in previous lessons when we constructed perpendicular bisectors. And that makes what out here is a point then that they are both connected to. And so it says so we have a point outside there. So this point right there is the point that you'd want to put that sprinkler at, is the perpendicular bisector of each of those segments. That way you could see now as you drew a circle, you can put a radius here. If you draw, you put your compass point on this sprinkler part and your pencil here, you could actually draw a circle, and that would be a radius there of perfectly finding that point then. So it says find the point where the perpendicular bisectors intersect. This is the center of the circle, which is equal distance from A, B, and C. So it's all equal distance from each of those. So I just wanted to show you that one so you're aware of it, and it might come up again a little bit later. Alright, so go ahead and finish up your 10.3 assignment, and I'll see you guys back in class.